Hello, everybody that come here. Thank you for attend. If you have any question, please write in the chat box. We will very likely to answer you during the meeting or after that. It is in order to keep all the sound around clean to hear the presentation. Thank you very much to be with us. We can start, please, Dr. Machado.
Well, hello. It's a great pleasure for us to be here and share with you something completely new and something that we hope you will appreciate at a very heartfelt level. As you can see, just our little icon in our picture here in the front on our very first slide illustrates the challenge that all of us have in making products at an industrial scale. We start with a beaker, we see in red. We have to wind up with our full-scale reactor or our full-scale mixing device, and we're trying to understand, will I get the same results? Am I going to be able to provide a sample to a customer from the beaker that actually will be produced at the same level in a full-scale reactor? Likewise, we may have to go the other direction, as you can see, which is I know the limited capabilities of my full-scale equipment, but how do I reproduce that limitation or that capability at the smaller scale? And this is what we're going to talk a little bit about today, with a new idea to actually transform your technologists and share with them the best ways and how we can do this in a unique opportunity. You know, why do we need to train with hands-on experiments and software? You know, so much of us are used to doing things virtually now, and we've lost sort of touch with that hands-on approach. Well, we're human, that's why. And because we're human, we have to actually engage in things at a fundamental level. Let me go a little further. You know, we hear things, and soon after we hear them, it's not long after we forget. Well, many of us who have children will understand this very intuitively. They hear something, and soon after you've asked them to do something, they forget. But you know, when they see things, or when we see things, we remember them better. Humans are visual. We see things, we understand things at a very fundamental visual level, and then we remember. But what does that do? It's almost like watching someone make a cake. We've watched them, I remember how they did it, but can I really do it? And that's where the unique part comes in. When you yourself have to go bake that cake, for example, you then understand the nuance that's required in how you provide the eggs, the flour, how you do things. It's that hands-on approach that uses all of our senses, our mind, our eyes, our ears, our hands, the equipment, and then we understand what we can do. And this is what we want to bring to you in this new offering, the School of Scale Up. Now, why the School of Scale Up? Well, you know, I've been involved in almost all of these industries over my entire career, and I know the new challenges that are coming to us. You know, they're asking us, management is saying we need to increase productivity. There's much more competition worldwide that we never had before. We have the internet, we're sharing ideas, sharing products, and we need to understand, okay, for example, how all of this comes together. We need to do it quicker because of the competition. There's the pharmaceutical industry where we're making new chemical products. We're involved in scaling up to existing equipment. In biotech, a brand new area in many regards, but also an old area because we've been doing fermentations since the beginning of time. But now fermentations are getting to a higher level. We're making unique proteins in the biotech industry, and we have to have very, very careful mixing technologies to bring those to fruition. In the specialty chemical area, we're looking at all kinds of very interesting chemical reactions and involving often multiple phases, catalysts. In formulations, we need to bring the materials together to get the correct viscosities, whether you're making hand cream or lotions or formulations for food products. All of these require very careful mixing technologies. And even in the electronics industry, where we need extremely precise techniques to make materials that have very high levels of quantitative and qualitative control. So these are our goals, and we need to do this quicker, faster than ever before. And so we need to have a very educated technology team in our companies. Now, you all have resources. Everyone's got some lab reactors, you've got pilot scale reactors, and to try to get you to change all this at this time, well, this is what you have. And so with the existing equipment that you have, what can you get to the next level of productivity? How do I have to change the way I operate in order to produce the products that I'm going to be able to sell? Well, we need to think a little bit outside of the box, okay? You just can't transfer a simple recipe to someone. We need to understand how that recipe changes with the scale. What are the new methods that you need to solve these very practical problems, to scale up things and to scale them down as well? Well, you need some hands-on training because we are human. And that hands-on training, which is how to use the software, how to start things up on the software, experiments, what do I do differently? How do I set up my lab reactors, my pilot reactors? Why do I choose a particular RPM rate? Understanding this in a fundamental level is really important. You know, we designed now a simple test experiments, which are some are demonstrated in the literature, to show how mixing influences your process challenges and how you can overcome those limitations. So in a lab reactor, you could run an experiment, you understand the results, you analyze this with the software, and then from that software, you begin to understand, aha, this is the critical component of my process. And it's seeing that, it's getting the raw data, it's working with the raw data, converting that into useful information to create incredible knowledge that allows you to be successful. Training has to be intuitive, insightful, and practical. It has to be fundamental. You have to feel it. You have to understand it. And so this hands-on training, making it accessible to all people, technicians, chemists, and engineers at all levels, okay? And this increases a number of things. It increases our skill base. It also increases our intuition and how we work together, our communication skills, because we've actually done the work itself. So what are we going to do? And what are this idea of School of Mixing? Well, this is our concept at this point, and we're working to advance it. But here's where we are at this point. We're anticipating 12 participants. Those participants would organize in 4 teams of 3, okay? Each team would conduct one of these experiments in a vessel selected at your site. It could be a lab reactor or something larger. We'll provide you with the actual experiments. Pretty simple. Salts, dissolving salts, some simple reactions with iodine experiments. All of these chemistries are simply available. You will receive, for example, a package. This is the requirements for the chemicals you need to purchase. Very simple. And the experimental techniques. Then SOS, the School of Scale Up, we're going to provide you with the software, and we're going to bring the data loggers and the instrumentation with us. It's a small set. We're going to have some temperature probes, we're going to have some conductivity probes, pH, and also a UV-Vis, small UV-Vis analyzer to analyze some of the chemistries that are going on. We'll set up those tests to your particular site. So you would give us some feedback. We have a 20-liter, a 30-liter, or a 50-liter vessel, whatever it might be. We'll provide you with how much chemicals we're going to need to do those simple things, salts, whatnot, and then everyone will observe the experiments. So as the experiments are occurring, the class will come in. Then one group will be assigned to doing the experiments. They'll be getting the experiments, and they'll be collecting data, and then from that data they'll do some very simple analysis using Excel or whatever software they may have. Excel is really all that's needed, and from that you'll take the data, you'll compare it to VisiMix calculations, we'll make the adjustments to match, we'll look at how that scales up. And each team will get a unique scale-up challenge for their problem. Okay, so you're going to wind up with a really practical problem with a real chemical reactor. So we'll provide you with, here's the chemical reactor that's available industrially, and then how do you do that scale-up challenge? How did you use the data that you required? Day one, we're going to introduce ourselves, and we're going to provide you with some very visual concepts. The first thing we're going to do is share lots of videos. This is what mixing looked like. I want you to have an intuitive understanding when we say things about whether you're using one type of impeller or another, when something is a fast reaction or a slow reaction. That intuition that you have from the visual observation is going to be very important and foundational. VisiMix is going to show you how to very quickly set up the vessels and how you set up the problems in their software. Okay, and it'll talk about how you do the geometries, you put things in, you match the data, you analyze it, and understanding the impact of scale up. Experiment one is one of the foundations of all mixing processes, which is what's the overall macro mixing? How do things actually come together to become homogeneous? Experiment number two can be heat transfer, for example, with basically a few thermocouples, not thermocouples, excuse me, PT100. We're going to show you how you can do simple heat transfer analysis and get some crude calorimetric insight into your process. We're going to use the data for scale up, and we're going to have that one-on-one support. So as the teams are working in their little groups, Moshe and I will be going around, we'll be talking to you about what we do. We're bringing tons of experiments. I have 38, 40, actually 40 years of industrial experience across many technologies. So we're going to be able to help you with the problems that you're working on. You're going to get data. This is school. You're going to have homework. Okay, so this is not just you come, you listen. You're going to be doing things with the software and the data. Let me give you an example of a problem that we will encounter. So here, for example, we're going to get some macro mixing data. We have a large vessel. It's about, I think this was a 100-liter vessel. And what we're going to do here is try to understand, how do I get mixing data for a vessel that's kind of like, a little bit unusual in the sense that there's no baffles, but rather off-center mixing to eliminate the need for baffles. And we want to understand, how do I get mixing data? So here's an example of what we would actually do. So we would set up the reactor. This is the setup that you would provide from VisiMix. This is the geometries, the off-center mixing, the size of your impeller, what type of impeller, locations, angles, etc., type of vessel. And one of the amazing things about VisiMix is you need to think of VisiMix. This is fast. This is a calculator. Imagine that you could plug numbers in to a system, your geometries, and immediately, okay, wind up with amazing levels of information and data. So this information tells you really what is going on in your mixing process. It's not just telling you yes or no, it's giving you the details so you can compare. Because as engineers and as scientists, at some point, our visual information has to become data and numbers. Because as scientists and engineers, we communicate, we do all of our processes by using numbers. And VisiMix is the calculator that gives you those numbers. So for example, on this page, you may identify, for example, here's our geometry on the left-hand side, and we could understand the turbulence. We're going to get information about the dissipation, that's the average across the vessel. We'll understand what is it like near the impeller. As you notice, it's order of magnitudes higher. That can become very relevant as to where you put, for example, your feed tubes, as an example. We're going to understand what's the time of micromixing. When do things finally diffuse together to become one homogeneous, chemically homogeneous system? We'll understand power. We'll understand all the different type of information regarding, what is the impact on the torque and etc. So with this information, we now can identify the variables that are critical for our particular process. So here's an experiment that we might do. You'd have a vessel, we have conductivity probes, and depending upon the size of your vessel, we have small ones and large ones. We would insert those conductivity probes. In this case, it's quite simple. We just add water to a mixing salt solution. If you have high viscosity systems, we can add methyl cellulose. That will increase the viscosity, for example, or we can add glycerol, depending upon if you have a lab reactor or a large one, however we design the experiment for you. Now we just record the conductivity changes under different conditions, and then we analyze our data. So here, for example, is an example of the data that we got by adding these salts in different ways at the top of the vessel and the bottom of the vessel, and then we also compared that to VisiMix. And I want to bring out some very important points. Number one, what you can see from this diagram, where on the left-hand side I have our relative conductivity change that occurred with the addition of the salt solution, and then we have the actual data in the red and the blue, which are the measurements of conductivity, depending upon where the addition was made, or excuse me, not where the addition was made, but where the conductivity probe was located. And then we have a first order model, which we can use by just doing a simple Excel spreadsheet analysis of the average data. But more interestingly, we have the VisiMix prediction from the bottom of the vessel. And as you can see, we actually predict some of the higher level peaks that occur at the bottom of the vessel when we have such a conductivity change. And this is the result of the type of mixing that's occurring in the vessel. It matches quite nicely, and so now we have confirmation of how we can actually scale that particular vessel. And with that information, we now know what the macro mixing was and how we can use that data for the next level of scale up or scale down. Quite simple, quite basic, but really important, especially when you're doing it hands-on. So the VisiMix software training, let's say for day 2, we're going to have 2 different experiments that day. One, and this could be in 2 different vessels. We bring the computer, we bring the data analyzers, quite straightforward. There's a dissolution of salt of different crystal sizes. So typically we're going to have a small and a large size, and we're going to measure what's the difference as we dissolve them. How does that compare to the data? Here's a general problem. I'm dissolving a solid. How quickly do I add the solid while it is dissolving and make sure I don't add it too fast? I have seen many examples in industry where people know the overall saturation solubility, but in the industrial scale, they add things too quickly. Things sit on the bottom, they form lumps, bad things begin to happen. So knowing the dissolution rate, it tells you a lot about how quickly I can add something and how well I can suspend those solids. Then we'll have a gas liquid training, which is quite simple. The CO2 will come from your local, distributor of CO2 for beverages. It's pretty straightforward. There'll be a sodium hydroxide solution, and we're basically going to measure the uptake by analyzing how the pH or the conductivity changes in the vessel itself. Pretty simple. But this tells us a lot about our gas liquid mixing in a vessel, and then from that we can compare that to the predictions by VisiMix. We'll have the one-on-one support for data analysis and software. You'll get your homework. You'll work as a team on your next scale-up problem. Here's an example that I want to share. Just how do you measure mixing salts of different sizes? So we'll provide you with these detailed photographs that show you this is the salt that you're dealing with. I'll bring the microscope with me if you so desire, looking at the problem. Looking through the microscope itself, do your own analysis. Pretty inexpensive, off the shelf. It goes right USB to your computer. We have a conductivity probe, and we're going to measure how quickly the conductivity changes. So one of the nice things about VisiMix is we can do a couple of things. We'll show you, for example, how you can take an off-center mixing problem and convert that to a baffle problem. So what you do is you look at the fundamentals of the mixing problem in the off-centered system. And then you say, I'm going to go ahead and make a model for a baffle. So the point of this is that not every software package or something that you actually obtain can solve every single problem. I mean, you could make an endless variety of things. So we'll show you how to use shortcuts, okay, that allow you to convert one system to another to solve particular problems. This is really important. I've never met a software package or any solution that covers all bases. If it did, it would be an unending number of options, and the software would take forever to scale up. You would be waiting for days. And you need data quickly, you need data right away, and how do I do this in an efficient way? And this is what we'll be training you with it as well. How to use things, how to make those shortcuts, how to analyze the problems firsthand. And that is the foundation of the course, to teach you about how you actually do things. And it's going to be very dynamic. So this is a class. It's just like there'll be training early in the morning, then there'll be experiments toward the afternoon, gathering the data, analyze the problems, and be ready for some homework. Okay, and then you will be graded. Okay, I'm just sort of pushing that a little bit. That's a bit of a joke, but no, you will have to understand how it's coming. So with this system. Once again, you can gather all these fundamental information, and I'll learn a lot about, you can put in your large particles or small particles, how long it will take to dissolve. And if we look at the lower left-hand corner, we see the time of complete dissolution for this particular problem says around 1 minute, the largest particles around 72 seconds. So we're in that 1 minute time frame to dissolve that quantity of material. Well, let's go see what actually happens, and that's what we'll be comparing to. So here's the experiment. As you can see, you have the conductivity as you add different amounts of salt, and the conductivity changes. We actually even see a temperature change, and we understand that that conductivity is proportional to concentration. We can determine that from the data, and then more importantly now, here we go. This is the VisiMix models. So VisiMix will actually give you insight as to the dissolving problem, for the system. And what you see here is that in green, this is for our smallest particles, and then in red for the largest particles. And then here's the average experimental data from the conductivity, and we can see that we can bracket this problem very nicely. And this is really what VisiMix brings to the picture. It shows you that I can take real data, I can compare it to predicted information, and now I have confirmation of what I need to do when I change my process. Okay. Now, if you're adding material if it takes about 1 minute to dissolve, I don't want to add the full charge of a solid, for example, all at one time, because it may just settle to the bottom, because you also have to compare this with the ability to suspend. And that's a separate type of calculation that's done by VisiMix as well. It'll tell you, are my particles even suspended? And we can't add things faster than they're suspended. Otherwise, you wind up with big challenges. The same thing applies to catalysis or any system, such as crystallization, for example. You don't want to crystallize things faster than you can suspend them. You don't want to have more fundamental crystal mass in your process compared to what you can suspend. In the lab reactor, you might do it one way, but at the plant reactor, you may be restricted. Likewise, you would have temperature challenges. So this will compare, the heat transfer with, say, for example, in crystallization, how quickly I can crystallize things, how quickly I can suspend things, and we'll show how all this becomes related. So there's lots of problem solving that goes along with this simple piece of information that we've generated. Now, for fast reactions, they're even more interesting because a lot of times we have fast reactions. We don't think about that all the time. Let me give you a classic example. I've been involved in many, many processes where all they wanted to do was adjust the pH. That's it. Very simple process. And to adjust the pH, they used a concentrated acid or base because that was the most convenient and the most efficient. But what happens is that at that feed point, there's an extremely high concentration of acid or base. And so locally, things can happen. And if it disrupts the chemistry, for example, if you have nanoparticles, if you have, for example, in the formulation industry, where you're trying to adjust, for example, say viscosity very subtly with the addition of a bit of salt, not pH necessarily, but salt, all of a sudden that local area can see an extreme condition that has an impact overall, and that can be a problem. So this is one of the more classic challenges. We're going to share the Dushman chemistry, and that will help us to analyze that. That's just an iodine one, and I'll talk about that in a moment. So we're going to use this new software package that's called Chem. It's the new Chem software that predicts how reactions occur in the local environment near the feeds and how that impacts whether it will occur globally in the reactor or whether it will occur locally and what happens in that particular situation. Okay, whoops, excuse me. So the concentration gradients always form in real reactor systems. This is what happens. Is your chemistry really fast? Meaning, does it occur at the same scale of mixing? And does that matter? And when your chemical reactions, whether it's a pH adjustment or an actual chemical reagent, which is a very highly reactive material that you're using, like an epoxy or something like that, or acid-base type chemistries and amine neutralization, then you need to really be careful to understand how mixing impacts that overall process. Now, here is a simple example. And we're going to add, in this case, it's not the Dushman reaction, but it's something similar. We're adding iodine to a thiosulfate solution. And so we're beginning this process. As you can see, we have a very localized color. That's the iodine coming in, and it's reacting to form this dark starch reaction, but then the starch reacts eventually with the thiosulfate. But if you imagine that the dark color are byproducts being formed, you can imagine that this process is going through a variety of changes. As time goes on, what you'll notice is that cloud of byproduct is increasing with time, all right? Why is that occurring? Because the reaction mixing compared to the chemistry reaction is changing as well. And so our process begins governed by a very local concentration and a very local finite mixing called micro mixing. And at the very end, it's the large macro mixing that changes the product that we see. Now here we see the Dushman chemistry that we're going to be using. What we'll put in your reactor is a simple potassium iodide, potassium iodate buffer system. And when we add to that system, there'll be a borate buffer in there with these iodine solutions. And so as you add this diluted sulfuric acid, it will basically react with our buffer, or if the reaction consumes the buffer locally, it'll start reacting with the iodine and iodate to form iodine. And we'll be able to measure the iodine formation in your particular reactor, whether it's large or small scale. All these are aqueous chemistries, and as you can see, these are fairly innocuous materials. Obviously, there's some safety associated with sulfuric acid, but this is a very dilute solution, and not to be worried about that. I mean, from a large scale point of view, it's not concentrated. It's like a 0.1 normal type of sulfuric acid. So that will be very easy to handle in a laboratory. Obviously, all the appropriate safety would be required in all of this. And so now we measure the iodine, and that iodine tells us how this undesired reaction occurs based upon particular mixing events that are occurring in this vessel. That vessel will be the vessel that you tell us about, and we'll learn about that vessel ahead of time till we can put the experiment in terms of what you can do. Day 4 is going to be group presentations. So each group will have been assigned their scale-up problems, and they'll then give a presentation to the class on the fourth day. This is what we did. This is how we solved the problem, you know, in PowerPoint, however you want to give the presentation, and then we'll share it with the team, and you'll have that in your company to understand it. And this is what I really recommend is in the group that you select, it's not all your process engineers, that you select a variety, basically a diversity of people that would be on your teams, so that each team could have, for example, a technician, a chemist, and an engineer. That would be perfect. So in each particular group of 12 people, you'd have one technician, one engineer, and one chemist. That is going to be an amazing result for your company. With that hands-on training, the fun we're going to have, eating lunch, having dinners together, doing homework and talking about it, it'll be unbelievable, I guarantee it. So don't miss this opportunity. This is unique. No one does this. You can go online and see hundreds of different presentations. You can go, you know, sign up for courses. You can get textbooks. You can go take lectures. But what's unique about this is we're kind of condensing the school experience that you would have, let's say, even in a first year chemistry class where you have lectures and you do experiments. But we're going to do this as a team. And that team aspect of this is what makes this powerful and unique, and the hands-on will be something that you'll remember for a long time. And we'll guide you through this, we'll help you with the software, and you will be empowered in a way that you have not been empowered before. So with that, Moshe, I end my challenge here, and I look forward to, you know, all the people around the world that say, hey, this is really cool. We really want to try this out, and give us that chance to help you help your teams. And I'm excited to be a part of that. So Moshe, I guess I turn control to you. I hope this went
Yes.
well, and we'll take
Thank you.
questions. Yeah, and Moshe,
Thank you very much for this. Thank you very much for this part. We have here two questions that are main technical questions. The first is, could you explain how torque is important here?
How torque is important. Yeah.
Yes.
So torque is important when you're analyzing your impellers, for example. So if you here, let me give you an example. I was with a company not too long ago, and they had put at a maximum, okay, the RPMs they ran in their full plant reactor. Okay, it was so many RPMs. And when we did some scale up analysis, exactly like this, and actually at the full scale plant, we did a pressure analysis to understand mass transfer. What we discovered was that we needed to increase RPMs. There was no way that we were going to achieve the result they wanted in the full scale plant. We went back and reviewed the torque requirements. And so we compared the torque that we predicted to what the torque available in the mixing equipment. And we found out that that torque was available to the gearbox or to the motor that's going to provide mixing to the process. So torque is very important, especially with regard to the equipment setup itself. We discovered that we can increase this limit that they had put on the equipment, and we increased the RPM still within the torque capabilities and the critical speed of the impeller by doing the mechanical analysis on VisiMix. It gave us the confidence. We then compared that. We had to go through the safety engineer, and on the full scale plant, we did that, and it worked out extremely well, and we transformed what was a reaction that they never could get good yield with to one that they almost needed no more distillation. So torque is important for the equipment. But on a fundamental level, torque is used by VisiMix to create the momentum balance that is the foundation of their software, using momentum and using these measurements. So torque is very important from that regard. More important for sort of the equipment mechanical aspects, yeah.
Thank you very much. The second question here is, what would you recommend as an approach to overcome the limitation of mixing not being able to recreate the original vessel agitator to get those initial prediction needs? This is part of the knowledge that we provide, because once you know what is the the flow that we're generating and what is the model what we use in order to calculate all this momentum balance and internal knowledge about what is the connection between the mixing and flow dynamics, we'll be able to advise what will be the best way to continue to generate results that will be representative, will be reproducible, and will be enough good in a good mixing practice. The main idea is to generate this kind of knowledge that is integrative knowledge about what you know about the process, what are your capabilities, and what is the mixing parameters involved there. The meaning of the School of Scale-Up is exactly this. It's not only one question about how to use the software or how I will measure it. It will come, of course, in the details of this of your activities, but the whole idea is to give you a very comprehensive way to think in a practical way, and after that to apply it in different ways. But at the end, we have some specific details points that, of course, we will be happy to answer once you will be registered as part of the School of Scale-Up. But you're part of this kind of instruction. We're very happy to help you in some questions that you have during the time, or refresh the knowledge again after 1 year, or new people that will come to the company would like to have this kind of school again by training, fundamental training for the company. All of this we like to offer. We are developing this kind of concept, and we hope it will be good for you.
Yeah,
Okay.
absolutely. Yeah, just to understand what you can do it, and I think it's that one-on-one that you'll learn with Moshe and myself of, how do I solve this particular problem? It might be that you adjust your process, right? You may have to add things much more slowly, right? So there are always things in your control that you can do. Change the placement of a feed tube, for example. There are little things like that you'll learn. Okay.
Very good. So thank you very much. What I will do now is to give you, the people that don't know about VisiMix capabilities, in few minutes I will do some brief work about VisiMix. Okay, how we are doing it. Okay, so 1 minute I will transfer to my I hope you can see my computer. Can you see my computer in your screen? 1 minute. Yes. Okay. So what I will do in few minutes, I will show to you what we can do with the software. Okay. Good. As Ray showed us, we have different kinds of software regarding to the capabilities, okay, that we can have. So he mentioned Turbulent, okay, with different kind of installation of the software, of center, multiple impeller in the same shaft, even bubble columns, and some software that are able to explain us better about what is the mixing into the tank. So we have VisiExcel that transfer the data from VisiMix to Excel, and Scale Up, Scale Down, that is the software that connects between the, for instance, solid distribution, and which is the mixing parameter that are controlling these activities, like this, any kind of processes and unit operations. And we have a capability to do some evaluation of different scenarios in different equipments, and to generate some sensitivity analysis. This I will show to you now in 1 minute. The VisiMix software is a special software that combines the reaction rate with the physical approach of mixing, and how they are connected, the chemistry with the physics capabilities in the flow dynamics. And we know well that the size of the molecule is not the size of the fluid element, and this deviation can generate different kind of deviation in the homogeneity into the tank in different places in all the equipment, and how it can influence the realistic reaction rate that we see, and the yield and the yield and the selectivity that we can get. So this is the group of VisiMix parameters VisiMix software that we have. And of course, according to your industry, we will be able to provide to you what is required. If you are working in the formulation, of course, remember that you are sometimes working in laminar regime or nonlinear rheology, and you are using maybe high shear rate equipment. Okay, so these two software will help you in order to give you a complete idea when the viscosity and the rheologies are higher than the viscosity that will give us the regime that it will be a turbulent regime, go to laminar regime maybe, and for this we need a different kind of mode. What I will do now for you is to open the software and do some round, exactly what Ray explained. I will do some round. I will start with the lab. I will go to scale up, and after that I will show to you how we can do sensitivity. It will not be more than 10 minutes. So I will open Turbulent. Sorry, I open the one. Turbulent 25. This is a new version, the latest one. And the first to do is to feed the data of the lab. Okay, so I click new and give a name of lab. And what I will get here is the minimum data required to start to calculate mixing parameters. So I will select less a beaker, okay, a simple beaker in the lab, okay. When I click OK, the software asks me the dimension, so the diameter, the total volume, and the actual volume that we have inside my tank. Once we click OK, the software asks me we have some buffers, no buffers. Even if we don't have buffers, maybe we have some probe. And in the lab, maybe it's enough significant in order to generate some kind of a buffer action in the flow. So I will use, for instance, one of the two, let's say 2 pH and temperature. The width will be 10, the distance from the bottom will be 20 millimeter, and the distance from the wall will be 10. So we have like these two. Once we click OK, the software asks me, okay, different kind of impedance you have, completely axial, completely radial, between them, some hydrofoil generic equipment, some other kind of equipment that is different than axial and radial, and some glass line equipment. Anyway, you can customize by using alternative impeller and power knob. It can be single or multi-stage. I will use a very typical one that is pitch pedal. Simple and typical one can be multi-stage. In the lab, normally we have only one. For fermenters, we have two like this turbine, but it is the same idea. Once we click OK, the software asks me data about the impeller that we are using. The diameter, the number of blades, the pitch angle, the width of the blade, the distance from the bottom, the rotational speed, and in the lab we need to be high velocity in order to be in turbulent regime, and the motor power that is only to protect your equipment. It is not, we are not using it in order to calculate the mixing power. We know according to the geometry and all the data what will be the mixing power. We protect your equipment because if the mixing power is higher than the motor power, you will not be able to use the equipment. Maybe you can calculate, but you will not be able to use the equipment. You have some problems with the electricity and the safety operation equipment. Now, once we click OK, we fit all the geometry and the operation. We need to fit the process. The minimum data for the process is density and viscosity. So we'll use density and viscosity that can be Newtonian or non-Newtonian media. I will use Newtonian in its case. In one, it's like water. And once we click OK, this is my tank ready to use. What we can do, we can calculate many parameters. You can see, like Ray explained, all the hydrodynamics. You click, enter, and get results about the mixing power, the circulation flow, the vortex dips. If we go last menu, you can calculate here the torque that we discussed before that. And we can continue to calculate, for instance, flow patterns, okay, how the flow is moving in the tank. We can see these flow patterns in 3 dimensions by generating a file for a viewer, that is viewer 3D, where you will see inside is fluid elements moving in the tank, okay? And you see how fast is moving. We can reduce the video velocity. We can reset and add the position. For instance, I want a position here, the other position here, another more fluid elements, and we can run them together. An intuitive way, people that don't know about mixing parameters, they can see how is the connection between them in a very fast way. You see a few seconds, it's not taking a long time. We can calculate the local mixing that we explained before that, okay? The maximum The average, you see that it's far. This explains the diffusivity and the local mass transfer. And after we know all the position in time, we can calculate the dynamics by mixing times. This is the macro mixing time, that is time required to generate 99% homogeneity in the integral way. But we have the local mixing, that it is the two fluid elements converging in one place to generate local homogeneity. And the circulation, main period of circulation, is some way to take in consideration the feeding position, the capability to express this material into the tank. Okay, once we finish to do it, we can go to, for instance, fill some solids. So we calculate and we click some solids, and we want to know the actual distribution. This actual distribution is the density and the viscosity of the liquid. We need the concentration of the solid, the density of the solid phase, and the particle size, 100 to 300, dB50 and dB95. And now what we will see is what will be the relative concentration as a function of the place. In this case, it's from the bottom to the top. You see you have 15% more material in the bottom than in the top. So in this way, you can see here, you have all the results that were required, and maybe you are happy with this. This was the process that you developed in the lab. You want to go to the production step. So what to do? Now you can go to scale up, scale down. In scale up, scale down software, what you see is we bring the data from 1 liter. We ask what will happen, for instance, in 6,000 liters. It gives a bar geometry similarity. What will be the order of magnitude of the diameter of the tank? And if I ask what will be the velocity required to generate the same suspension of the actual distribution, when I click there, the software selects for me which mixing parameter is the controlling parameter, what is the velocity expected to have in the production step, and all the main important mixing parameters that we know it can control reactions, mass transfer, gas, liquid, liquid, solid, liquid, 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 crystallization, all what we can think. Now, once we do it, we click OK, and it is for me the best prototype based on geometry similarity. If I calculate here the solid distribution, I will get exactly the same solid distribution, but because we're in a big equipment, the material that we're able to take up is going well, but we have not enough local mixing in order to take material from the bottom. This is the meaning of complete suspension is questionable. When we click OK, you see exactly the same solid distribution, but we have solids in the bottom. How to solve it? Okay, it's very simple. We can change the RPM, but we can go to sensitivity analysis and go to liquid solid mixing and ask the software at the same level of media by changing the rotational speed from, let's say, 33, that was what we did, to the maximum in this equipment maybe would be 120 RPM. Calculate me what is the solid distribution in all the equipment. We finished to calculate all. Now we did 12 times the same calculations, and now when I click display results, what I see is all the results regarding to solid liquid when we change the RPM in all the way. And you can see, for instance, complete or incomplete suspension, that we find a place exactly between 33 to 40 that we have from incomplete to complete dispersion. Okay, so but we have all the solid distribution for every run. And if you click all in one, you can see not only this, you can see other mixing parameters, okay, that are related to the solid liquid. So the mixing power, the macro mixing time, and more. So we have now the data from the 1 liter, the factor for 6,000 liters that is completely similar. What we can do is to change the equipment to a different equipment by changing, for instance, the tank diameter from elliptical bottom, okay? Let's say my actual equipment is like this, okay? And I have 5,000 liters inside. And now we have 4 baffles, okay? And my equipment is, for instance, two multi-stage, and the distance between these two multi-stage about 600, 700 millimeter. And now when I click OK, I have my data ready, and I can click the solid distribution. You see now my power is a problem because we have two impellers, and immediately we'll get the solid distribution is about 30% with no problem with the solid distribution in the bottom. Okay, So if I want to see all these results together, the lab, the best prototype, and the production, we can come to process analysis, select the lab, the option, and the best prototype. And what we'll see there, we'll see not only the sensitivity analysis, we'll see the comparison between the lab, the prototype, and the production. And in this way, we have all the idea in our hands in combination with the measurements we did, and we know now what is the environment, all the mixing together, that it is the main important change that you're doing when you go from lab to the production, because you can fix the same raw material and the same procedure, and you have some idea about what was the best configuration to generate good results in quality, purity, and operation. You will be able now to know to measure it in a good way and to get conclusions about what will be the best step. Of course, we can do scale down. Okay, if I come in the same button, okay, and I come to scale down, you see we have 6,000 liters, and we can go exactly to the same way to one liter, for instance. It gives me the geometry similarity, and by asking the solid distribution, it will give me what is the velocity that with the similar velocity. Okay, so it is vice versa in the same way. This is the way that we can work with the software. Of course, all the reports is straightforward that are inside, and this will be the way to work. We measure, we calculate, we think together what is the main thing with us, the process, reaction, dissolution, crystallization, what is the main important point there. And this will be the way to go to the scale up. And this is the school, exactly how to integrate all together in a practical way, not only theory. That we wanted to show to you is here the theory. So this is what I wanted to show to you now here. And I see that you have some questions that I will read and raise with me. I hope he's open his microphone. Let me only check. This microphone is open. Yes, and I will read the questions. I will try to answer. Okay. Yes, formula to calculate torque and how to calculate it in VisiMix. Okay, this is part of the that in the help of VisiMix and the review of mathematical models, we have the explanation for every calculation we do. But remember, it is a complete model. It is a software that solves the flow dynamics into the sterile vessel based on a huge data of phenomena that we cover in order to give you a representative result. So this is not only a simple formula. It's a completely solution of the momentum flow by velocity into the tank in a very smart way. How do you model with 2 mixers in the tank? We have a software for up to 5 different mixers in equipment. In the software, we have 2 motors that you can use and 3 motors, one for the scraper, one from the center impeller, and one from the rotostator. All of these we have in the models. You will need to use 2 or 3 models depending on your process. Thank you for you to attend this. Thanks for this informative webinar. Thank you. This is interesting. Could you please help me with the annual license code? Please contact us. We will manage with you what is the cost of the school and what is the cost of the software together, and we will manage, of course, all of it regarding to your requirement. Okay. Yes, and the last question. German, how are you? What would you recommend as an approach to overcome the? Okay, this we discussed before that about the how to connect together. Okay, so thank you very much. You have more questions, please contact us, VisiMix, or contact Dr. Machado. We're very happy to answer your questions, to discuss about what are your requirements, what are your needs, in order to try to generate for you some kind of offer that will be relevant to your team regarding to the field that you are working. The mainly knowledge about VisiMix work, about a school of scale-up school of scale-up was present here. This is fundamental for every kind of thing. It is not only dedicated for chemical reactions. It's for every kind of operation. The fundamental that we provide after we thought deeply about it are represented in these 5 experiments. Okay. Of course, you can have deviations about it, and we can, after we finish the first step, we can go to other step about to try to think about your specific process. But it is the base, the fundamentals that it will give you a capability to understand the role of mixing, how it's important to implement in the scale-up fundamental stories to generate results that will be good in the productivity, purity, and avoiding problems in the operation. Okay, so any more question? Very good. So thank you very much, Ray, to be here. Thank you very much for the audience, and we are very happy to hear from you, and contact us whenever you want. We will be very happy to discuss about how to progress in this School of Scale Up. Thank you.